In the name of Allah, the Merciful, the Beneficent. Assalamu alaikum. I'll explain the second part of my presentation, which starts from hydrogen production from biomass. And at last, the sixth step of producing hydrogen, which is the ammonia decomposition. So let's start with hydrogen production from biomass. As we all know that the term biomass encompasses a variety of organic entities resulting from the synthesis of biodegradable and non-biodegradable substances through photosynthesis. It includes plants, animals, microbes, and other residues, along with forestry and agriculture waste like agriculture remnants, food waste, biofuels, etc. Originally, the meaning of biomass expanded with the introduction of the idea of renewable energy during the oil crisis. And because of this transformation, biomass is resulted as a sustainable material, abundant in supply, and cost effective, and leading to its widespread utilization in fuel and natural resource production of the hydrogen. The production of hydrogen from biomass has become a topic of significant interest from the 20th century. And the categorization of biomass includes algae, solid municipal waste, and wood. And they all are contributing to carbon dioxide absorption during their growth phase. Biomass is considered as a highly carbon neutral resource, and the studying say that comparing wood and microalgal biomass indicate lower ash percentage in wood biomass. From production of hydrogen using biomass, the first we will use solid municipal waste. And to meet agriculture need and supply organic matter, solid municipal waste compost is frequently implied in large quantities in agriculture. It is a common method to enhance the decomposition of organic material in waste in the inclusion of organic material. The solid municipal waste creation process is not an easy process to overdo. The solid municipal waste process is favored due to requirement for less space, oxygen, and residence time. But the most challenging aspect for this process is the production of large amount of sludge. However, which increase the organic content of the sludge makes it more suitable for fermentation. In a research paper, Chune et al., a scientist, utilized wastewater treatment plant in Flint to investigate hydrogen synthesis from organic material. He tells that production of green energy while reducing greenhouse gas emission is not a promising effect nowadays. So, one widely adopted method for transfer municipal solid waste into a sustainable product like electricity or hydrogen is through gasification. And various solid waste gasification facilities are operational in nowadays. And these are planning stages on a world level. Compared to incineration, gasification is effective and environment friendly. However, some contaminants emitted during the gasification process, such as hydroxide, chemicals, tar, halogens, etc., possess environmental challenges and may lead to operational issues. So, this table evaluates the structure of gasification by the municipal solid waste in several roasting investigation under various testing conditions. So, at temperature 700 to 900 degrees Celsius, steam catalytic gasification process produces 36.98% of hydrogen from solid municipal waste. At temperature 900 degrees Celsius, steam catalytic with air gasification process produces 32.8% of hydrogen. And at times 50 degrees Celsius, steam catalytic and air mode of gasification process produces 40% of hydrogen production. The second method of producing hydrogen from biomass is using food waste. As we all know that food waste constitutes a substantial portion of municipal solid waste arising from the production of consumption stages of food. Managing food waste presents significant challenges. And countries like Japan, India, and South Korea generate hydrogen between 624 and 635 million tons of food waste annually. Basically, numerous studies have explored hydrogen production from food waste. For example, combined effect of salinity inoculation on thermophilic lactobacillus genomic and physiological profile from hydrogen generation. The findings showed a 7 to 56% increase in hydrogen output with pre-treatment inoculations. This is a review table of hydrogen production from food waste. First, from kitchen biocare, we can produce 955.3 milliliter of hydrogen. From olive peel, we can produce 840 milligram of hydrogen. Waste water and paper, we can produce 325.7 milliliter of hydrogen. Lime clay and paper, from lime clay and paper, we can produce 138.6 milligram of hydrogen. And from kitchen biocare and paper, we can produce 480.51 milligram of hydrogen. The third is to use of biomass algae to produce hydrogen. And according to estimates from the International Agriculture Organization, the global production of fresh algae ranges from 150 to 600 tons per hectare annually, resulting in 12 million tons of dry matter each year. And these 12 million tons of dry matter each year produces a lot of hydrogen. Unlike traditional energy sources, algae do not rely on hydrocarbon but utilize excess carbon dioxide in the environment. And this unique characteristics ensures that utilization algae for energy does not result in a net increase in carbon dioxide emission, which is contributing to the restoration of the Earth's natural thermal environment. This is the hydrogen output of and concentration of algal biomass. For example, an algal family chlorella, which is a micro organism, produces 48 to 63% of hydrogen content. The other one is Gelidium, which is also an aquatic organism. They produce 66 to 67.3% of hydrogen content. The sixth method of generating hydrogen is by using ammonia decomposition, and it is the most widely used method in the past decade. And there has been extensive exploration of ammonia decomposition processes and technologies, which are primarily focusing on producing carbon dioxide or COX-free highly purity hydrogen. The ammonia decomposition reaction achieves equilibrium conveying of 99% and 99.7% and 400 and 500 degrees Celsius temperature respectively. Despite these high conversations, the presence of residual ammonia in the produced gases necessitate additional high-cost hydrogen purification technologies. So let's have an overlook of how we can produce hydrogen from ammonia. The first reaction will be known as the thermocatalytic decomposition of ammonia. Understanding the thermodynamic parameter of a catalytic reaction is crucial for designing industrially relevant catalysts. The ammonia decomposition reaction is endothermic and temperature dependent, requiring thermal energy from hydrogen and nitrogen production. And due to the equilibrium nature of this reaction, high temperature are necessary for efficient ammonia decomposition. Thermodynamic conversion of ammonia analyzed using the Gibbs free energy minimized method is presented in this figure. The reaction strongly depends on temperature ranges between 200 or 250 degree to 450 degrees Celsius with conversion of planetary above 450 degrees Celsius temperature. Therefore, ammonia decomposition is highly reliant on kinetics at the high temperature. Now we will see the kinetic aspect of ammonia decomposition. In 1942, the first systematic study on the thermocatalytic decomposition of ammonia over iron-based catalysts demonstrated that ammonia desorption from the metal surface is the rate determining step for hydrogen production. However, the complex dependence of the ammonia decomposition rate on temperature and pressure remain unexplained yet. The rate determining steps in ammonia decomposition depends on reaction condition and the catalytic nature. The adsorbed ammonia molecule is initially dehydrogenated through nitrogen-hydrogen bond cleavage, forming an adsorbed hydrogen species and a metallic nitride. Subsequently, reaction between hydrogen and nitrogen atoms produce gaseous H2 and N2, respectively. Under pure ammonia conditions, nitrogen-nitrogen bond formation with a bond enthalpy of 580 kilojoules per mole becomes a rate determining step. Factors such as catalyst choice, economies, long-term stability, product purity, and efficiency need consideration for the ammonia decomposition reaction. This is a schematic diagram of ammonia decomposition. As we can see that we have a catalyst, or on the catalyst surface, ammonia firstly will be absorbed, the dehydrogenation process will occur, and nitrogen and hydrogen will produce. And this hydrogen will be stored for further use. So this was all about how we can produce hydrogen from renewable resources. Now we will see how to store this produced hydrogen. And the primary technological challenges in realizing a sustainable hydrogen economy has been development of effective hydrogen storage system. When considering hydrogen storage techniques and materials, several factors must be taken into account, including high pressure, temperature, taken designs, gravimetric and volumetric hydrogen densities, energy efficiency, refueling time, durability, cost standard, technical maturity, and life cycle and efficiency analysis. Firstly, we will see how we can store hydrogen in the form of compressed hydrogen. Compressing technology provides a direct approach to hydrogen storage. However, this method is inefficient in terms of both volume and weight consideration, and resulting in a relatively low density of 42.2 kilojoules hydrogen per meter at 69 megapascal for compressed hydrogen. The second method of storing hydrogen is by using hydrogen in the form of liquid. Liquid hydrogen emerges as a promising hydrogen storage due to its high purity and density, nearly 800 times greater than uncompressed hydrogen. However, the need for an extremely low temperature, relatively minus 2500 or 253 degrees Celsius for H2 liquefaction, results in substantial energy consumption. The third method of storing hydrogen is in the form of methanol, because methanol presents advantage for both hydrogen storage and carbon dioxide hydrogenation, aligning with the power to product concept. Methanol can yield hydrogen through various processes but raises environment concerns due to carbon dioxide release upon use or degradation. Additionally, the separation and capture of carbon dioxide incur high energy consumption and operational cost. The fourth method of storing hydrogen is in the form of ammonia. As we have seen in the ammonia decomposition process, efficient hydrogen carriers should have higher hydrogen content, convenience in storage and transport, and easy breakdown into hydrogen when needed. Ammonia stands out due to its high hydrogen content, carbon-free nature, and ease of liquidation under mild conditions. Now we will see what are the environmental impact of hydrogen production. Another facet explored in this study involves assessing the reduction in carbon dioxide emission, which is achieved by generating ammonia through green electricity, as opposed to employing other methods. It is noteworthy that the global reduction in carbon dioxide emission could be more substantial if the generated green electricity were initially utilized directly within the grid, therefore decreasing fossil fuel consumption for electricity generations. In an optimal scenario where the integration of generated green electricity into the grid It could potentially reduce worldwide carbon dioxide emission up to 2.8 times more than if the electricity were used for green ammonia production and subsequent export to other cities or areas. From a grid administration perspective, supplying green electricity to the national grid becomes attractive only when the electricity is provided with minimal or no fluctuations. This aspect merits further investigation in a separate study. While contributing to global industrial decarbonization, this approach may not fully exploit the potential of these resources due to the inefficiencies inherent in hydrogen ammonia production processes. Now, let's study how the hydrogen potential is reliable in achieving net zero emission target. Basically, the production of hydrogen fuel from hybrid renewable energy resource holds the paramount or holds the potential to meet the carbon summit target by 250, utilizing technologies that yield net zero greenhouse gas emissions. Despite this, there is a scarcity of studies specifically delineating the scope of utilizing hybrid renewable energy systems. So for this purpose, various technology including fuel cell and electrolyzers offer opportunities for generating hydrogen energy and converting it into electrical energy as needed. Efficient energy storage systems play a pivotal role in mitigating the intermittent nature of renewable energy resources. Nevertheless, there is a limited body of research available on the integration of hybrid renewable energy resources, specifically for the hydrogen production. Despite the importance of energy storage, there is a dearth of studies on the summation and optimization of green hydrogen production. Furthermore, no research has been conducted on a regenerative solar wind hydrogen hybrid system that operates independently for the grid, ensuring zero emission. This represents a notable gap in the existing body of knowledge, emphasizing the need for further exploration in this innovative and promising area of producing hydrogen gas. Now, I will conclude all my review article, or what I have conclude from the whole article. In addition to its conventional role as an industrial feedstock for ammonia, methanol, or hydrogen production, hydrogen is emerging as a novel energy vector. This study comprehensively addresses the technologies employed in generating hydrogen from both conventional and renewable energy resources, exploring aspects such as its utilization, storage, transportation, and redistributions. The practical challenges associated with implementing such as system are thoroughly examined. Renewable energy sources including solar, wind, geothermal, hydro, biomass, and other are considered for hydrogen production. Given the intermittent nature of some renewable resources like solar and wind, hydrogen emerges as an optimal choice for use as fuel or storage medium. Owing to its advantage and the availability of carbon-free alternatives, hydrogen is gaining increasing global attention as a viable fuel and a distinctive energy carrier. This review article evaluates diverse environment for renewable hydrogen production, considering system design, cost, infrastructure, and efficiency improvements. Each method of hydrogen production using renewable energy is discussed, taking into account the associated efforts. Additionally, the report conducts a thorough analysis of the infrastructure, transportation, and storage of hydrogen, acknowledging both the progress made and the remaining challenges. Furthermore, the possibility of enhancing existing fossil fuel-based hydrogen production facilities by integrating carbon capture and storage system is explored, aiming to absorb emission and transition towards green hydrogen. And at last, these all are the references from which I have written my review article. So thank you. That's all from my side.